Hi everyone. Today we're going to keep working on section 6.2. So all we're going to be doing today really is getting more practice finding integrals using geometry. And then I'm going to show you the function on your calculator that will allow you to use your calculator to find the value of an integral. So first we're going to do kind of, a little mini investigation that's going to we're going to work through using geometry and some properties of functions and integrals. So here's the idea. Suppose you know that the integral from 0 to pi of sine x dx equals 2. And remember, what this is telling us is that the area between the sine curve and the x-axis from the interval from 0 to pi is equal to 2. Okay, so we're taking that as our given. And so it says with that information, what we know about integrals and areas, what we know about graphing curves, we're going to determine the values of all of these following integrals on the page. Okay, and we're going to sketch a graph of each time just to see kind of what's going on at each step. So the first thing I'm going to do is graph this portion of the sine curve from 0 to pi. So hopefully this should be a quick, easy exercise. Sine of 0 we know is 0. Sine of pi over 2 is 1. And then sine of pi is also 0. So there's my sine curve from 0 to pi. And again, the integral just means we're taking the area between that curve and the x-axis. And we know that that value is equal to 2. So we're going to use that to find some other integrals. So in number 1, it asks us to find the integral from pi to 2 pi of sine x dx. So let's go ahead and sketch out what that would look like. So sine of pi is 0. Now 3 pi over 2, we know the sine value is -1, and then sine of 2 pi again is 0. So it looks like this. So now we're always talking about the area between the x-axis and the curve. So we're trying to find this area here. So the first thing that hopefully we notice right away is that this area is under the x-axis, which means it should have a negative value. So we know the value of that integral is going to be negative. Now here's where we have to use properties of functions. I know that this area should be the same area encompassed here. It's just negative because it's under that curve. So it's going to be the same value of 2, but a negative. So the area under that curve is going to be -2. Again, because these are symmetric pieces of the graph. Now we're going to kind of put these two together for the next one. If I look at the integral from 0 to 2 pi now, so I'm sketching in my key points, and I'm going to put in the curve. What we notice is we have a portion of this area, and I'm going to use two different colors just to highlight this. We have a portion of the curve here, which is a positive area because it's above the x-axis, and a portion of this area is negative because it's below. Now again, the absolute value of these areas is the same. The same area is encompassed by each of those curves in the x-axis, or I should say each of those pieces of the curve, but one's positive and one's negative. So those are going to cancel each other out, and that integral is going to give us a value of 0. Now, let's look at the next one. So this one's interesting because now it's the integral from pi to pi over 2. So I know that the sine of pi is 0, and the sine of pi over 2 is 1. So I'm pretty much looking at this area right here. So the first thing I notice is, well, it's half of this piece here. So that makes me think that this is going to be 1. However, because it's kind of going backwards here, we're integrating from pi to pi over 2. That makes that value negative. Again, because we're going backwards. If we were integrating from pi over 2 to pi, we would have a positive 1. But when we're going from pi to pi over 2, that's going to be -1. And that'll be an important property of integrals that we'll talk about maybe in a couple days. All right, so let's keep going with this. See if we can calculate a few more. For number 3, now we have the integral from 0 to pi of 2 plus sine of x. So now this 2 I know means I'm going to shift my graph up 2. So at each point, I'm going to shift it up 2. So sine of 0 is 0, but now I'm shifting it up 2, so my point's going to be here. Sine of pi over 2 is 1, and let's see, I'm going to extend this a bit. Sine pi over 2 is 1. If I shift it up, I'm going to get a value of 3. And then again, sine of pi is 0, but if I shift it up, I'm back at 2 here. So now I actually have all of this area here. So I'm still between the x-axis and my curve. So now I have this portion here, and I should have used colors here. This portion here between the sine curve and my y equals 2 has an area of 2. But now I also have this area down here, this square area. And so that, because it's a square, is easy to calculate. That's going to be, actually it's not a square, excuse me. Its base here is pi, and its height is 2, so it's a rectangle, so its area is 2 pi. So this value of this integral is going to be 2 pi plus 2. So the area of my rectangle plus that area here, which is 2. All right, next one is negative pi to pi. Okay, so we're going to graph our curve. Again, at negative pi, I'm 0. If I have negative pi over 2, I'm going to have negative 1. 0 is 0, pi over 2 is 1, and pi is 0. So very much like number 2 above, again, since I have a negative and a positive area, the value of that integral is going to be 0. Okay, so then the last one we're going to look at is the integral from 0 to pi of cosine of x dx. So now here I have cosine 0, I know is 1, cosine pi over 2 is 0, and cosine of pi is negative 1. So I have this area here. And so hopefully we can all see, because we have a positive and negative, there's symmetric portions of that graph, or equal areas trapped between the curve and the x-axis. That's going to be an area of 0. So again, this was just using some basic geometry and what we know about those trig functions to calculate these areas, but you'll see later on that a lot of what came out of here will actually be some important properties of integrals down the road in a couple days. So for the rest of the video, we're going to just do a few more geometry examples just to make sure we're all pretty solid on that. And then I'm going to show you the function on your calculator that can calculate these integrals. Let's see. I'm going to skip a couple here. We've done this semicircle example before, so for this right now I'm going to skip that. Let's look at number 2. So right here I have my function is the absolute value of x, and I would expect that that's a function we're very familiar with. Right, we should all know, hopefully, that that's going to give us this V shape here as our absolute value function. And so I'm integrating from negative 5 to positive 6. So what I get are some triangular regions here. So again, we're using geometry formulas at this point to calculate these areas. So I'm going to have 2 areas here, 2 triangles. And again, don't be thrown off because we're in the negative x-axis here. Since this area is above the curve, we should have a positive area. So on my left-hand side, I have my triangle, my area is 1/2. The base of that triangle is going to be 5. And now if I'm the absolute value of x, the absolute value of negative 5 is a positive 5, so my height's 5. So I have an area of 25 over 2. For my second piece here, second triangle, I have 1/2. My base is 6. And again, absolute value of 6 is 6, so my height is 6 as well. So I get an area of 18. So now 25 divided by 2, I know that's just 12.5. So the value of my integral, or that total area, is just going to be the sum of these two areas, or 30.5. All right, let's go ahead and look at one more. This is something we talked about the other day, about graphs that have discontinuities. And again, the idea here is that that discontinuity does not affect our ability to find the area using an integral, or in this case, using geometry formulas. So if I look at this function, I notice that there's a discontinuity at x equals 2. And so I'm going to take a look at this function. X squared minus 4 I know is x minus 2 times x plus 2. That's over x minus 2. So what I notice is I have a removable discontinuity, or a hole, at x equals 2. But for our purposes in terms of graphing this to find the area, we know this is just the function x plus 2. So I'm going to go ahead and graph that. So let's see. My y-intercept here is going to be 2. I'm going from negative 4. I probably did not leave myself enough room here. Negative 4 plus 2 is a negative 2. So negative 4, negative 2. And then I'm going up to 3. 3 plus 2 is 3, 4, 5. Okay. So I've got some points here. I'm going to just use my ruler to connect those. Okay, so there's a graph of my function. Now I do have a removable discontinuity at x equals 2, so really there's a hole at x equals 2. But again, for the purposes of us being able to find the area, the only thing we really have to watch out for is that we have a negative area here over this interval, and then a positive area over this portion of the graph. So remember that integral subtracts out that negative area, so we'll have to make sure we do the same when we're calculating it. So for my positive portion, I have 1/2. My base is 1, 2, 3, 4, 5. And that height there, we said that function value was 5 as well. So we have 25 halves, or 12.5. Now for our pink area here, we have a negative area, so I'm going to have a negative 1/2. My base is 2, and the height of that triangle is also 2. So I have an area of negative 2 for that portion. So now when we add those together, we're really doing 12.5 plus a negative 2, or subtracting that out. So that gives us a value there of 10.5. All right, so now that we've done a quick review of some of our geometry formulas and how that works with area, what we're going to do quickly is just show you on your calculator how you would be able to calculate integrals. Now, some of the syntax may vary based on whether or not you have MathPrint on your calculator. So I'm going to show you how it looks on mine and how to access this function, and then I can show you in class if you have specific questions about how to work with your syntax. So on the calculator, to get to this function, we're going to do math, and you'll see if I were to scroll down, math 9 is fn int. So I'm going to just write that down here. So it's math and 9, and that looks like this. Okay, and so if I were to click this now, coming from the main menu, I don't scroll down every time. I just do math and then type in 9. It takes me right there. And so here's what it looks like on my calculator. And again, I can walk you through if this is not how it looks on yours. So you'll see our integral notation here. So I have this, and then I have 2 boxes. Okay, and so just this kind of could serve as a quick review of integral notation. Remember here what it wants is your lower bound of integration. This is going to be our upper bound. This is what we call our integrand. It's really the function that we're integrating. And here we're going to put our variable of integration. So here's what it's going to look like. We'll just do a couple quick examples to see how this works. So let's look at part A. So again, I'm just going to clear this. So for review, it's math. I'm going to go to 9, and I get my integration here. So I'm going to do -1, because that matches my lower bound. Use my arrow key, type in 2. My function is x times the sine of x. And then now my variable of integration is just x. It matches the variable that I put in for my integrand. And when I hit enter, I get approximately 2.043. Okay, and again, just to make sure we're all using the program correctly, we're going to do a couple more. This next one, we're going to have to be careful about how we use parentheses. So again, we're going to do math 9. I have from 0 to 1. And now I'm going to have to be careful. I have 4 divided by the quantity 1 plus x squared. So I'm going to make sure that 1 plus x squared is in parentheses. And again, my variable of integration is x. So I get approximately 3.142. Okay, for our last one, we'll just do this last one here. Integrating from 0 to 5, I'm doing e, here we go, to the negative x squared dx, and I get an approximate value of 0.886. So that's all for today. You'll do a station maze to kind of work through some quick problems tomorrow, and then an extra worksheet as well. See you tomorrow.